Hi, let's do an example with some hydrogen atoms. I already opened the folder that has our refinement files in it. You're going to notice that there's one extra file in here, the FAB file. That's generated by plate and squeeze, which is a program for masking disordered solvent, and we're going to talk about it later. But for now, you can just consider that the FAB file is along for the ride, and we don't have to worry about it. I'm going to go ahead and run a quick refinement right now to generate a res file with QPeaks and everything. And at the same time, I'm going to come over here and open the ins file in a text editor. We'll take a look at the res file in OLEX, and we'll kind of get oriented with the structure. Now, the first thing you're going to notice is this is our first example of a molecule that has only half of itself in the asymmetric unit. In other words, the second half of the molecule is going to be generated by the symmetry of the space group. I'm going to do that by typing grow into OLEX, and now we can see what the molecule is. It's a hexacopper cluster. Each copper is capped with a phosphine. Each phosphine is a diphenyl isopropyl phosphine. I mean, we can also see that these ligands are taking up a lot of space in our view here. So I'm going to get rid of all the carbon atoms by typing kill $C. Now it's a little bit easier to see. This is expected to be a hexacopper hexahydride cluster, and we can see that there do appear to be six, well, I can say there are 6 difference peaks. They're about 0.8 electrons, which is consistent with a hydrogen, and they're capping 6 out of the 8 faces of this kind of squashed octahedron of copper atoms. Since we're expecting hydrogens, it's a very reasonable interpretation. We're looking at them in the difference map, and the first thing we can try is just putting them right in there and see how they refine. We won't overthink it too much. We'll just put them in and run a refinement and see what happens. Now remember that 3 out of these 6 QPeaks that we're looking at, they're generated by symmetry. So we want to use the sort of the original 3 out of those 6. So we're going to see which ones those are. I found one here. If you find a symmetry generated atom, then the symmetry code that generated it is going to be listed in the little pop-up window when you hover on the atom. So that's a convenient way of seeing if something is original or symmetry generated. Or the other option is I can just type fuse, and now as long as we can see which 3 QPeaks we're interested in, here's our 3 hydrogen atoms. So let's insert them in the ins file. I'll put the 3 hydrogens after the 3 copper atoms. For now, I'm going to treat these just like any atom. I'm going to refine their coordinates, and I'm going to let their isotropic ADP refine as well. If it turns out that the ADPs aren't stable, then we can find a way to restrain them or fix them. Okay, that's all. So this is a free, totally unrestrained hydrogen atom refinement. Go ahead and run that. We can see that the R factor improved from, well, now it's 3.16%. The before it was 3.30%. So that definitely is a significant improvement for just 3 hydrogen atoms that we added. Let's take a look. Okay, they didn't go flying away somehow. They stayed pretty much where we put them. I'll get these carbons out of the way again. Let's analyze the bonding geometry on here. I'm going to do that by just measuring these bonds one at a time. I'm gonna call these types of bonds that kind of go around this uncapped tricopper face. I'm going to call these equatorial bonds, and these other bonds that go sort of perpendicular to the uncapped faces, I'm going to call these axial bonds. So just so we have a way to refer to them. I'm going to go around and measure the equatorial bonds first. We have 1.75, 1.7, 1.72, 73, 72, 1.69. Okay. All 6 of these are between 1.69 and 1.75 angstrom. And the other 6 are related to these 6 by the inversion center in the middle of the molecule. So I only need to measure 6 and make sure that 6 independent ones. For the axial bonds, the same. I'm going to measure 3, and we know that the other 3 are inversion related. We have 1.91, 1.86, 1.85. Okay, so these bonds are all consistent within what is it, 0.06 angstrom or so. And that's just about the best accuracy that you're going to expect to see on hydrogen atoms in general. One other thing to check is the isotropic ADPs on these atoms. We're going to expect that they should be slightly bigger than the equivalent, excuse me, from slightly bigger than U equivalent, which is sort of the average dimension of the 3-dimensional ellipsoid on the copper atoms that the hydrogens are connected to. So U equivalent for this copper is 0.019. We'll check one more just to make sure they're consistent. We have 018, 018. So the hydrogen should be slightly bigger than that. We have 0.038 for this one. We'll measure the other 2. 038 again, and 050. So these hydrogens, their displacement parameters are significantly bigger than the coppers they're connected to, but not unreasonably so, not outside of the range of what's reasonable for hydrogen atoms. And you have to get used to the exact amount of consistency that you expect to see in hydrogen atom structural parameters. But in general, they are a little bit more all over the place than other atoms. It's because they're not as strongly scattering. So if we have a range of bonding distances of 0.06 angstrom and ADPs that are maybe slightly bigger than they should be, but they're within a couple hundredths or so of the reasonable values, we can be pretty happy with that. But we want to get some practice restraining these hydrogen atoms with different techniques. So I'm going to do a couple different things here to stabilize them. Looking at the chemical symmetry of this problem, we can imagine that all of these equatorial copper hydrogen bonds should be equivalent, and all of the axial ones should be equivalent too. So maybe we can set one target distance for the equatorial bonds and another target distance for the axial bonds. That's a good example of a free variable that we can use. we only want to restrain the symmetry-independent atoms, so we don't need to generate duplicate restraints for these symmetry-generated ones. I'm going to delete those 3 hydrogen atoms just to get them out of our way, and now we can figure out what 6 equatorial bonds we want to restrain and what 3 axial bonds we want to restrain. The axial bonds are easy. These are just coppers 1 through 3 and hydrogens 1 through 3. We should consider renaming these hydrogens so that they each have an axial bond to the corresponding copper. So right now copper 1 is bonded to hydrogen 3, and we're going to take H3 and put it right under copper 1 and rename it as H1. Copper 2 is bonded to hydrogen 1. So we're going to take hydrogen 1, put it under copper 2, and rename it as hydrogen 2. And then copper 3 is left with hydrogen 2. We're going to rename it as hydrogen 3. We'll rerun this refinement quickly just so that the names are updated and we don't get messed up. I'm going to kill the carbon atoms again. Okay. So a problem we have here is we want to restrain some distances that involve a symmetry-generated copper atoms. So for example, hydrogen 3, what? Oh, I didn't save it. Kill the carbons, grow the structure, get rid of the 3 symmetry-generated hydrogens so that we don't get confused. Okay, now we're all set. And as I was saying, hydrogen 1 has bonds to copper 3 and copper 2 generated by inversion. So how can we restrain that bonding distance? We're going to use something called a CuHgood. I'll show you how to do that. I'm going to put all of our restraints underneath the copper and hydrogen atoms. I'm going to write equiv $1. This means I'm defining the first symmetry equivalent code. I'm going to write the symmetry generated coordinates exactly as they're represented by OLEX. So the first symmetry equivalent that we define is 1 minus x, 1 minus y, minus z. We can see that this is an inversion center because all 3 of those coordinates have a minus sign in front of them. So inverting all the coordinates, that's an inversion center. We can call symmetry equivalent atoms by attaching this symmetry code to the end of the name. So I'm going to fix the distance between, I need to get these names up here. There. I want to fix the distance between hydrogen 1 and copper 2 generated by that symmetry operation. Defix, we haven't decided what the distance is yet, so I'll put a XXX. H1 copper 2 underscore $1. What this says is fix the distance between hydrogen 1 and copper 2 transformed by the symmetry operation defined on the CuHg1 line. Now we'll put all the other equivalent distances on the same line. We have hydrogen 1 to copper 3. Hydrogen 3 is bonded to copper 1 and copper 2. And finally, hydrogen 2 is bonded to copper 3. And it's bonded to copper 1, transforms by the symmetry operation. So H2 copper 1 underscore $1. Okay, that's our 6 independent equatorial copper hydrogen distances. And if we did generate the other 6 in this view, we would just see that for hydrogen 1 copper 2 equivalent 1, the other bond would be hydrogen 1 equivalent 1 bonded to copper 2. But it's not independent from this distance, so we don't need to restrain it separately. We'll restrain the 3 independent axial bonds, but that's not so hard to do. H1 copper 1, H2 copper 2, H3 copper 3, and we named those hydrogens cleverly so that we would be able to write those restraints easily. Okay. So what is the distance that we want to restrain this to? We want to make them all equivalent, so I could make this a SETI instruction instead, and now these 6 bonds are made equivalent. But instead, I'm going to fix the distance to a free variable. So this says free variable 2 is the target distance for all 6 of these bonds. And likewise, free variable 3 is going to be the target distance for the axial copper hydrogen bonds. So we'll go up to the FVAR line. We'll add 2 new free variables. The target for the equatorial ones, we know that's about 1.7. That number is going to get refined. And for the axial ones, it's about 1.9. Okay, we'll save this, repeat the refinement. You know what? As long as we're here, as long as we're fixing things, we can also try a group isotropic ADP for the hydrogen atoms. That's another good way of stabilizing things. So free variable 4 is going to be our group isotropic ADP, and I'm going to put that at the end of each hydrogen line. Okay. Oh, unset free variable for atom H1. That's the free variable for the isotropic ADP, which I forgot to add. ADPs are going to be about 0.04, so we'll start there, and that's going to get refined too. Okay, so we had 478 parameters before. Now we still have 478 because we took out 3 hydrogen ADPs, but we added in 3 variables, 3 free variables. Okay, let's see how consistent is this structure now. Kill the carbons, grow the structure, and kill the Q peaks too. Now we'll zoom in. Let's see, what did the ADPs refine to? This is 0.041. Obviously, the others are 0.041 as well. That's a good, reasonable number. How about the copper hydrogen distances? We have 1.73, 71, 72, 72, 72, 70. Okay, these are definitely more consistent now that we restrained them. We have 1.86, 89. Okay. take a look at the refined values for those numbers. Free variable 2, the equatorial distances that refine to 1.72. Free variable 3, the axial distances, refined to 1.87. And we already know the ADP is refined to 0.04. Okay, so it wasn't strictly necessary that we made those restraints because the structure was doing okay on its own. But now we have a little bit of experience generating restraints for hydrogen atoms. And we also have some experience working with symmetry equivalent atoms and generating restraints involving those. Okay, I think that covers everything for this model. One more thing to notice before we quit is the biggest peaks in the difference map will scroll up to the previous refinement results if I can find them. Here we go. Before we had plus 0.8, minus 0.3. So those are some significant positive features, and that's something to kind of get our attention. Now we have plus 0.5, minus 0.3. Those are the fact that the plus and minus are on the same order of size, that's reassuring to us. The fact that the absolute magnitudes of these are pretty small is also good for a structure containing the atoms that this one does. The R factor, we have 0.0462, and we compare that to 350 and 423. So we're not quite as small as the R int or R sigma for this data set, but we're in the ballpark, and we can also remember that we had some disordered solvent in this structure that's already been taken care of, and the existence of that disorder can increase the R factors a little bit. So we're not too concerned about that. The difference map is flat, and the hydrogen atoms are looking chemically reasonable. They all resemble each other, and they all have reasonable displacement parameters. So I think we can be happy with this model. Okay, thank you.